Is my voice coming? Voice test. Voice. Yeah, it seems like it is coming. Okay, everything all right? Let's check from the comments. Okay, thank you. And let's start. So this stream is about computer science field and the subfields of computer science. So what subfields exist in computer science field? What are the children of the science of computers, let's say? And we will also check job opportunities for computer engineers and computer scientists. So it is on examining industry and academia. By the way, I'm Ahmet and I'm studying in Boğaziçi University. I'm into computer science and machine learning for about 3-4 years. And in this time I have came a bit of way, let's say. I did a year of research on image processing. It's a subfield of machine learning, and I am currently working on natural language processing in industry, doing consultancy and products and stuff in a company that resides in İTÜ Teknokent in Istanbul. You can find me in this address or with my nickname in social media. So I will open this stream up with computer science fields in academia. So there are some images here for you to recognize some computer science concepts, but let's take a broad view firstly. Computer science is mainly divided in three main branches, and this is from Wikipedia. Because it's an encyclopedia, it gathers this broad knowledge well. So I took it from there, and we will examine all of these and give examples. What are these and how can we work on it, and why are they interesting, each of these subfields. And at the end of the slide, we will talk about the job opportunities and popular jobs, let's say, in industry. We will also talk on machine learning and artificial intelligence and the job opportunities there, but there was no time to make slides for them. So we will go, let's say, a bit on the flow in that subject. In computer science, we have slides. In AI and machine learning, we will go verbal. So let's start with the computer science fields in academia, and let's inspect what are these subfields. Let's focus on theoretical computer science first, and then so this is doing art for the sake of art. This is the theory, and this is where the most maths comes into play, and all these formal definitions and proofs and stuff. Most academic work is in here. And then we have an in-between, let's say, branch in which both applied concepts come into play, and there are also theoretical concepts. And that is computer systems and computational processes. So most academicians will do work here. And also most industrial work will be done here. And there is also applied computer science, which is a really interesting branch in my opinion, because it inspects how can we use all the things we learned in theory and these computer systems and processes and use them in basic research, in science, let's say. How can we use them in natural sciences, like physics and chemistry, and how can we use them in social sciences? And also, how can we develop value with them? How can we generate economic value with computer science? So that's why applied computer science, I think, is very interesting. But these other two are also very tasty, let's say, in terms of intellectual taste. And let's start with theoretical computer science and go deeper. So there are 4 subfields in theoretical computer science, and we will give examples to all of them, but let's first examine them broadly. Theory of computation inspects if something can be done with a computer. So we have a question of if I can do this with a computer, but not practically, theoretically. Can I do this given that all of the resources are available and I have a lot of money, a lot of computation power? Can I do this even then? Believe it or not, there are problems that we cannot solve with all of the resources in universe, and there are problems that we cannot solve even with infinite resources. They are insolvable by nature, and theory of computation inspects them, and that is why it is a very fundamental field of computer science. It changes our very fundamental understanding of if something can be done. So when there is a significant advance in theory of computation, it affects everywhere. That's why I wrote here, it points the way for almost all other fields. If something big happens here, then it affects everything else. It is kind of similar to these physicists' work. So Einstein found general relativity and special relativity and changed our fundamental understanding on universe. It amazed everyone and also changed many things in engineering. Also, de Broglie wrote, let's say, matter wave function in physics, and here is another experiment. What is this called? Two-split experiment. It also changed our very fundamental understanding on universe. So this is similar to that kind of physics in a sense. Let's go back, and now we will continue with information and coding theory. So an example on this is WinZip. WinZip compresses the information. What is compression? Compression is, we have a data, right? We have an image, and we want to make it smaller because we will transfer it. We want to make it lighter. And to do this in a cheap way, we compress it, but a very important thing while doing compression is we shouldn't lose information, or we should lose it minimally. So it is a hard problem and well-studied field, and it is very important. Almost everything that we see in internet, almost everything, every piece of data that is transferred is being compressed and decompressed on the way. So it is very important for accessibility. When the internet is slow, we rely on compression to watch videos, to get audios and get live streams or play games. Also, the blue screen here you will recognize. The blue screen is very frustrating for most of us because it tells us that our PC is broken. But it is actually a good thing, not a bad thing, because when this blue screen did not exist, we didn't even know why our computer got broke in software level. So that was even worse than the blue screen. Blue screen provides us information on why this happened and how we can solve it. And before the blue screen, let's say, while the engineers developing Windows operating system, they were thinking on how we can make this operating system so people will not get blue screen. So this is a very applied approach on coding theory, and it provides reliability to us. Whether a code will work or not work, and whether it will be efficient or not. This is coding theory. And information theory is on compression and other stuff. So these are just examples, and there are many other things to each of these fields, actually. So these two are done, and let's check the comments if anything goes wrong. Double slit, yes, thank you. Double slit was this experiment here. And let's continue with data structures and algorithms. Perhaps the most famous one here. Every engineering student almost gets data structures and algorithms because it is very fundamental, even in an applied way. Let me explain what I mean. So this is something that I wrote. It can be argued to be true or not, but when we think about it, every action in a computer, everything you do, every action you take requires an algorithm. You need to describe how will you do it. So it is very fundamental. Every program needs an algorithm. And it is also important in this sense. There are many ways of doing the same thing, but most of them work better than the others, both in terms of speed and quality. So it is very important to develop good algorithms. And while we take actions on entities, right? I add a friend. Adding the friend in Facebook is an action, but the friend is an entity. For every entity that I have in a computer system, I need a data structure to represent it. So everything that exists in computers needs a data structure, and every action we take on them needs an algorithm. That's why this is a very important concept and very fundamental, and is taught as the first class in most of computer science and computer engineering programs. Examples to this is graph traversal algorithms, which our guy here, Dijkstra, wrote one, an efficient one, and also dynamic programming. Graph traversal algorithms is on, I want to go from somewhere, let's say from Bob to Ted, how can I do it fast and efficient? Dynamic programming is about something else. While doing a big task, a bigger task, and while I divide it to make it smaller, let's say smaller subtasks, and this is called divide and conquer. While I'm doing divide and conquer, I sometimes redo some of the tasks, okay? Some of the subtasks are same of each other. While I divide and conquer, I sometimes do the same thing again and again. Dynamic programming ensures that I don't do the same thing again and again, but rather remember the past result and just get it from there. No need to work again. I already did it, and I can take the result from the past work that I have done. And these are the examples on data structures and algorithms. I didn't give an example on data structures. There are many, let's say linked lists, matrices, and data structures for graphs. Another thing on theory, programming language theory and formal methods. So I'm not very knowledgeable on formal methods. That's why I will give more examples on programming language theory. So there is a very sweet and not very popular, let's say, type of program. It is called linters. It is for the people that write code. Linters help us when we write code, and they tell us if we did something wrong or something that is not that good. And they check this with getting the text we wrote, the code we wrote, and analyzing it by dividing into, let's say, smaller parts and understanding what we wrote. Actually, without even linters, every code that we write is needed to be broken into smaller fragments, and then, only then, the computer can run it. Because computers cannot work on text. Computers only can run code, right? And while we transform our text, which is the code we wrote, into the program, into the ones and zeros, we need to parse the language. Parsing means transforming. We need to transform it and divide it so that the computer can understand it. So programming language theory is important to write efficient code, to write good code, and also it helps the programmers to do better stuff, to do stuff easier. These are the 4 subfields of theoretical computer science. And now we are done with this. Let's go back to comments and then come back here. Okay. Now we will continue with computer systems and computational processes. There are many fields here. They generate economic value, and they are also used heavily in academic research. And let's dive into them. So we don't have sub slides for these. We will inspect them from here. So we have a very popular field, and that is artificial intelligence. Very popular in nowadays, and many subfields under artificial intelligence. It is mostly about, again, doing things. It is very similar to algorithms actually, but there is a fundamental difference between algorithms and artificial intelligence. In algorithms, humans transfer their knowledge into rule-based systems. They write the algorithm in a rule-based way. They define the rules, do this, do that, then do this, do that. And then we have a working program. That is algorithms. But what happens in artificial intelligence? In artificial intelligence, we don't tell the program what to do exactly. We don't tell it like, do this, do that, do this, do that, do this in this way. We don't tell it that. We give it data and we teach it the inputs, let's say, the inputs that the program will take, the situation that the program is in, let's say, and we tell it the desired output, what we want from you, what you get first, and then what we want from you as the output of that input. We tell the program these two, and then program learns to do it in a way. But the important thing here is that it learns to do it. We don't tell it how to do it. And there are many subfields, as I said. In robots, it is a hard problem to move the robot arms or legs in the right way. Human body is so well, let's say, is such a well machine that we don't even think it is hard to move our hands or hard to run, but they are actually hard tasks. And let's inspect how hard it is by watching a video of Boston Dynamics. So what you see here is a very, very well working robot in today's circumstances, but you can see how hard for it is to stand up when it is kicked, right? So walking or even standing is a very hard problem. Look at all the coordinates of the joints and how it adjusts not to fall off, to not fall off. And it even does not know the coordinates. Let's say it does not know my knee is here, my feet is here. It can only measure the movements and then make predictions on what should I do now to not to fall off. It is very hard, and that's why even we don't know how to do it. So instead, we tell the robot, okay, when this happens, you should give the output of this, but I don't know how can you do it. So you should learn it by yourself. That's why we need artificial intelligence in this area. There are also chatbots. These are mostly algorithm based, by the way. They mostly work with algorithms, rule based, but there are also cases where we use machine learning. Okay, we need to fix this. This is the most things that I'm talking about here is machine learning. It is on learning. The intelligence can be gained via learning by itself, or we teaching it, rule-based teaching, okay? So this is rule-based teaching, and this is machine learning. This is mostly machine learning too. We don't know how to recognize faces. It is innate to us. We can do it, but we don't know how we do it. So we tell the computers, you should recognize this face as, let's say, Ahmet's face, but I don't know how can you do it, so you should learn it by yourself. It also applies to, let's say, fingerprint recognition or YouTube recommendations. So nobody knows how can we make Ahmet watch YouTube more. Nobody knows it. But we can tell the machine, okay, when you get Ahmet into the YouTube, you should make him watch more. So if you recommended some videos to Ahmet and he didn't watch them, then I will punish you. It's not good. But if he watched them, that's good. You should keep doing a similar thing. You should keep doing a similar strategy to make Ahmet watch it. So this is also with machine learning. This is artificial intelligence. And as I said, it can be rule-based learning or machine learning. Rule-based learning is algorithm-based, while machine learning is data-based. Let's come to the second computer systems and processes topic. It is computer architecture and organization, and a very sweet playlist exists in YouTube about it. Let's see what computer architectures are. So I want to build a computer, but how can I do it, right? Most of us don't even know how these laptops work. What components does it include? There are many components that computers include, and I can make a guess that nobody in this world knows uh, everything about a single laptop. It is such a big technology, such a complex technology, that a person can know everything about a single laptop. A person can at most know a component of a laptop, uh, let's say by heart, very well, but not all of the computer. So the reason that Ben Eater can do an 8-bit computer by himself is that an 8-bit computer is a very simple computer. In that case, the case which the computer is very simple, you can know everything about that computer with your heart. But in more complex computers, which are today's computers, you cannot know actually every piece that your computer includes and the insides of every piece, every component. But computer architecture is very important, and there is a term in Turkish, let's say, gathering a computer. You take the components yourself and then you integrate them, right? To make it cheaper than buying a whole computer. And this is the most simplest, actually, example of computer architecture. You need the necessary computers, a processor, a screen, and other things. So this is computer architecture, and you can work in all of these actually. All of these have both academical working fields and also in industry. So you can actually work in, let's say, ASUS and be a computer architecture specialist, because ASUS makes computers. In case of artificial intelligence, you can work in many companies. So what is concurrent, parallel, and distributed computing? It is about doing a task. So there are actions we take, right? We ask questions to computer and it answers. We can ask Facebook, who are my friends right now? I have 164 friends, but who are them? That's a question. That's a query we give to computer, and it gives us answers, friends lists, let's say. While we do any task, asking for friend lists or another thing, let's say training an artificial intelligence model, we can do it with one processor only, using only one processor, or we can divide this task so 10 processors at the same time can work on doing it. And it is very important because it buys us time. While I could do something in, let's say, a month with one processor, I can do it in one day with 30 processors, let's say. And that's why concurrent, parallel, and distributed computing is very important. And many of the large-scale projects that we see is actually running in a distributed way. Netflix works in a distributed way because it needs to provide you with content, but if Netflix's content would only reside in one location, let's say it resides in New York, okay? The data transfer from New York to Istanbul would take very long. you need to store it in a distributed way to make everyone reach it fast. So it's similar to doing subsidiaries with computing and also sharing tasks, okay? It is also important for reliability because when you do a task from a single central place, if that central place fails, so if let's say a server of Netflix is hacked, then Netflix should not be down. I should still be able to reach Netflix. But how can they do it? They can do it if they make their software in a distributed way and data, okay? Their content. So blockchain technology is fundamentally built upon distributed computing because many computers agree upon which information is genuine and which information is not. Also, cloud computing is very good for using many processors at the same time to do a big task. So we are done with these three and we are continuing with computer networks. What are computer networks? It is actually similar to a human community. Human communities interact with each other, right? We talk with each other. And why we need to do it? To make bigger things than us. If we need an action that needs 10,000 people, let's say if we need to build a structure that is very big, we need, let's say, 1,000 workers. But how can we make them work together? We should communicate with them, right? There needs to be a hierarchy. There needs to be managers and top managers upon them so that they can communicate in an efficient way. This is very similar to that. Computer networks facilitate for us the communication of computers. The internet is built upon computer networks. So everything you do in internet, everything you do in web is there thanks to computer networks. And how is my computer connected to a website in New York, let's say, or in California? How is Ahmet's computer, which is in Istanbul, connects to a website served in California? The easy, let's say, simplified answer is Ahmet's computer is connected to a server in Europe, and then that server in Europe is connected to America, let's say North America continent, via the transatlantic cables that goes in the bottom of the ocean. Okay, there are literal cables that goes from the bottom of the ocean to give us the internet. Okay, let's say Atlantic. Okay, so this is it, and they are very important. There are also recent work on doing this in another way. Starship, no. What was it called? Elon Musk Internet Project, right? Starlink. So how does Starlink work? How it works? Graph. Can we find it? We couldn't find it, but let me show you in a very simple way. So let's say this is the Earth, okay? And there are little satellites that rotate around the orbit of the Earth. Let's say this is Africa, and this is Asia, America, Europe, Australia, okay? There are little satellites that rotate around the orbit of the Earth so that we don't need these cables. These little cables that go underneath the ocean, we don't need them. What can we do? We can transfer the knowledge from US. Okay, this is not seeable. So it is transferred from US to satellite, and then satellite rotates or transfers it to another satellite, and the other satellite transfers the knowledge to Istanbul from California. Okay, this is another way to let's say facilitate computer networks, computer networking. And it is very important because it provides us internet and POS machines. You know, when we pay with credit cards, 5G networks, internet from phone, those are all computer networks. There is a very important topic that I have missed here. I recognized right now. There are operating systems which are Windows, macOS, and Linux. And actually, every phone, every Android phone, let's say, is a Linux machine, is a Linux computer. So our phones are not phones. They are computers. That includes phone functionality. And let's go back into comments. With script, what problems? Is there any problem? Okay, then I'm going back to the presentation. We presented computer networks, and let's talk about computer security and cryptography. Cryptography is about hiding knowledge, okay? I have a piece of information, but it needs to be hidden. Why? Because it is being transferred to somewhere, and people can see it. People can catch it and read it while it is being transferred. And I cannot make it, let's say, I cannot prevent people from reading it. I know that for sure people will read it, but I want to make it, let's say, unreadable or ununderstandable. When people read it, it needs to be encrypted so that people cannot understand what's inside it, okay? It ensures us this. And it is very important because many systems that humans work on need security, need privacy. And if we don't have cryptography, everything is out in the open, right? And computer security is about, let's say, building castles, building fortresses. I build a computer program, but I want to constrain how people act in it. Let's say I have a game, but I only want people to gain coins in the game if they do missions. I don't want people to gain thousands of points or thousands of gold whenever they want it, right? I don't want cheaters. But how can I make sure that they won't be able to? It is a very hard problem because the computer software that I have built is full of flaws, is full of little holes that people can exploit. Yes. So I need to patch those holes to make exploitation less possible. It is always possible, by the way. That's why computer security is very important, and many companies do not spend any money on it until they get hacked. So there are some very popular examples here. One example is Stuxnet, hacking of Iranian nuclear program. It is a very big use case of computer security, and it is one of the most complicated cases to inspect in the field of computer science. It's a very advanced work just to hack a machine. There is a 70-page long report, Stuxnet report, let's say. What was the... was it? It was a yellow and black antivirus software. But what was it? Was it Kaspersky or something? Anyway. Notes. Okay, I couldn't find it, but there is a Stuxnet report that inspects how did this virus work by a very famous antivirus company, and it is very interesting. SCADA was a challenge by anonymous people that was just a fun challenge on cryptography and hiding things and finding hidden messages, let's say. You can check it in YouTube. Blockchain is also built upon cryptography, just like distributed computing, because in blockchain, oh, where is it? I cannot see right now. Okay, in blockchain there is a function called hash, and hashing is a very important component in blockchain which ensures the blocks to form a chain. The chains between those blocks are actually the hash functions, and hash functions work with cryptography, so that's why it's very based upon cryptography actually. There's actually a famous virus, WannaCry. You can also inspect that one. What about databases and data mining? So databases, what are they? In the previous years, let's say before the 20th century, in the 19th century, we used paper to write notes, right? Paper notes. Let's say scientist, historical photo. Okay, let's say American president signing legislation. Okay, history. Okay, so what are these people doing? They are reading information and writing information on papers. There are many things that we wrote on papers. Information about companies, information on how much did the company earn, information on the legislation of countries, information on academic knowledge, information, let's say, similar to encyclopedias. What else? Even code was once written on paper, and we were storing information in paper. But now, in today's world, we don't. We do not use paper anymore. What do we use? Instead of paper, we use databases. So that expression can give you the sense of how important databases are. It replaced paper, basically. And data mining is, let's say, going to a public library and opening books and gathering information from there. It is similar to that, okay? Data mining is essentially going around the internet or any other source and gathering the information that I want. Web scraping is an example of data mining. So what are the examples that the databases are used? Online banks. Every transaction, every piece of information about you and your financial history is being put on databases. Social networks. Everything you post, every action you take, every friend you add, they are in databases. Online games, let's say, why progressive? Because it's not like you get into the game and when you get out, you lost your progress. It's not like that. It is saved into the database, your progress. Your progress is being kept in the database. Everything that needs to be noted in today's world is being noted inside the databases. Another area is computer graphics. Computer graphics, I actually found a picture, right? It was here. Look at the teapot. The teapot is a very famous example. It is like the hello world of computer graphics. And computer graphics is essentially drawing in computers. By drawing, I also mean playing videos and generating, let's say, CGI in movies, right? There are effects, special effects that's being made in movies so that we can make a dragon act in the movie. It is both about drawing and also showing the drawn content. It is important in programs that needs to show you something, and that's the programs that you draw something. Okay, there are CGI, computer generated images in movies. There are architectural design programs used by architects. Let's say there are simulations that simulate how the light will reflect when a given light setting and an object, metallic objects. What is matte in English? Okay, what was matte? I guess opaque. Okay, opaque objects, metallic objects. How the light will reflect. Let's see. Unreal Engine light simulation, right? This is a world, this is a room that does not exist. But we know how the light would reflect from the floor to our eye in this world. This is a simulation and it includes an intense amount of computer graphics. So we are done with this and done with the two main sub-branches of academic computer science and computer engineering. And let's come into applied computer science, which I also worked in. Remember I said I was doing research about image processing. That was on medical imaging, imaging the tumors, let's say imaging cancer, and working on those images. So it is a field of applied computer science. How can we use computer science to make, let's say, medicine easier, or make chemistry easier, biology easier, pathology easier? Let's come into that, but there is no slide for that, I guess. So let's talk about it from here. Let's check the comments before. Okay. Yeah, small flickering I was not able to solve for a long time, for about 2 years now. So if anyone can help me on that, I would appreciate. So computational science on other fields of science, on physics. Let's say in a given situation, how will a particle act? This is a question. There are particle simulations, let's say. There are simulations that work for quantum particles, and there are simulations that work on elements when they form compounds. There are simulations that work for molecules. There are simulations that work for organic molecules and how they will act in biological systems. All of these are applications of computer science in physics, chemistry, and biology. Flight simulators, airplane simulators, AutoCAD, right? AutoCAD, but with mechanical properties. AutoCAD heat simulation or aerodynamic simulation or resistance simulation. Let's check one of these and then check the others. How will this component inside a car, let's say, heat? Because I need to make sure if this little triangle heats above, let's say, 100 degrees of Celsius or not, because it might melt and I don't want it to, because then the component might break. And because I cannot try it every time, I need to simulate it. And that's where I use computer science in mechanics, right? What else? I can use it in aerodynamic situations to burn less fuel in my car. And on, let's say, fluids that flow. That's fluid dynamics, another thing. Okay, we couldn't find anything about this, but let's say stress tests. So when you make a component and it is being used in a bigger structure, let's say there is weight on it, and each point in the component is getting stressed by the weight. It's holding the weight, and that's why it is being stressed. And if the stress is a lot, it might break. I need to simulate that stress too. I think these are very good fields for mechanical engineers, if they are interested in computer science, to work on. There is social computing and human-computer interaction, which I am not very knowledgeable on, so I will not talk on that. And there is software engineering. Software engineering affects many people, right? And we use algorithms there, we use computer networking there, because we need algorithms to do every action in applications, mobile applications, let's say. And we need computer networks in every application that uses internet. So we use those knowledge in doing software. That's why it is applied. So as we have covered all of these, all the things in academia, as far as we know, let's say, we can go into industry and talk about popular jobs. And then I will, I guess, finish it, because if we talk about AI too, it will be very long. But I can take questions on AI, okay? Ask anything you want on AI or computer engineering or computer science, and I will answer it. So what are some popular jobs for computer engineers or computer scientists or people that are simply interested in computers and people that have learned things about computers? There is the, let's say, most popular type of job, and it is software developer. It's on writing the logic of a program. So if you click the add friend button, you have a list of friends, right? It adds that person, let's say Mehmet, to Ahmet's friend lists. That is a logic inside a program, inside Facebook, and a software developer needs to write it for it to happen. That's why it is one of the most popular jobs in, let's say, computer industry or technology industry, let's say. Database administrator. So we have papers and we have folders that keep the papers in. So we need a librarian, we need someone to organize those folders. And whenever we need the information inside them, the person will bring us the information. In this case, this person is not the one that brings us the folders, but the person writes the code that brings us the folders, okay? And it also writes the code that builds the shelf to keep the folders in. The database administrator also decides on how big a folder will be, how long the papers will be, okay? Those kind of stuff. User experience designer is, let's say, designing the visuals, okay? Keep your eye on my mouse right now. My mouse goes to this reload button, and when my mouse goes to the reload button, it shines, right? This is user experience. It is a way to tell me that if I click right now, then this button will work. But if I click right now, that reload button will not work. It's a visual cue for me to see it. And it is very important because it makes us use the software easier. If I wait even more, it brings me an explanation. It says reload this page. These are very important little details in software that make our lives easier, and it brings competitive advantage to, let's say, Google Chrome when compared to another browser. The design is very important. This reload button could also be in the, let's say, middle bottom of the page, right? They could put this into here, but they did not choose to. Why? Because they have designers working, and the designers think, and they say, for a person, for a normal person, it's easy to find it in the left upper corner. They assume this and put it here. So these are all this text box, these tabs, the little crosses here, they're all taught in a very intense way. And also they have their own code. You need to tell the computer that this button will exactly be there for it to be actually be there. A software tester ensures that when I click this, it will work. Because as humans, we build things and they fail. When you build something for the first time, or even for the 100th time, it will fail. Software tester tests this in an intense way and makes sure, okay, let's say it tells, the software tester tells the software developer that, hey, this software fails here. Can you fix it? That's what they do. And development operations engineer gets the code that software developer writes and makes it downloadable. Download Google Chrome. So I click to this, okay. Okay, now download it, please. Can I see it? Okay, I cannot see it, but let's assume that there was a file here being downloaded, okay? So for the code to transform into that downloadable program, you need to compile it and then, let's say, make packages of it, make it usable. That's what development operations does. Transform code into programs, usable programs. Business analyst simply inspects how we will use Google Chrome as users and tells software developers and UX designers, let's say, you should make incognito mode very easy to use because many people want to use it. And how does the business analyst know it? The business analyst inspects how many times we click on this button. So business analyst has data and uses the data to think of and design better designs. The product manager makes sure that these goals are being reached. So they act as a manager. Data scientists inspect this data, let's say similar to business analysts' data, but actually more complex data. It can be images, it can be voice. Let's think of Amazon Echo or Google Home Assistant or Siri. It can be voice data, it can be video data. They inspect these kind of complex data. There is security engineer, which we talked about. The companies don't pay to these people only until they get hacked. Network engineer ensures, let's say, POS machines work. When you pay with credit cards, they ensure that the POS machine emits a signal to nearest, let's say, what is it called? Base station, is it that? Radio station, okay, wireless tower, cell tower. They ensure that the signal goes to the cell tower and then the cell tower returns back a signal, payment accepted or payment not accepted. Hardware engineer makes sure that my screen works or my keyboard works, because so each button here is working with an electrical circuit, right? When I press this, two conductive metals touch to each other and there is an electron flow, and hardware engineers make sure that all these electrical circuits are designed in such a way that when I press 3 buttons at the same time, they won't interrupt each other. They will still work even if I press many buttons at the same time, let's say. So they design hardware, every kind of electronical material that you can think of. And there are also game developers which are very popular, and they work on, let's say, simulations. Each game is a simulation, right? And they work on game engines which are, let's say, Unity 3D, Unity Engine, let's say. They work on Unreal Engine. or they work on much simpler engines that they write themselves, okay? And there is that. Now we have covered the popular jobs and academic fields. We didn't get into the AI since 1 hour and 6 minutes passed since we began to this presentation. But if you have questions on machine learning, artificial intelligence, or computer science, I can answer to your question, give answers to your questions as far as I can do. So that's all from me, and I will be waiting until, let's say, 10 past, and if there is no question, I will close the stream. But if there are questions, I will go as far as I can do. Okay. You're welcome. I hope it has been, let's say, it has been useful to you. I hope that people learned things. You're welcome, and thank you for listening. And thank you for the kitchen comments. Let's wrap up in these 2 minutes, and you think of questions. If anything comes to your mind, you can ask again. What did we cover today? We covered fields of computer science and some popular jobs that we can work on. So there are fields in academia, theoretic fields, let's say in-between fields, which include theory and applications, and more applied fields, let's say. We talked about these theoretic fields, let's say middle fields, and the applied fields. We also talked about some popular jobs and explained what they do, so that we have an idea on what we can work on if we study computer science or computer engineering, and what do these people actually do, and how does the systems that we use every day work. Who are my idols in computer engineering? Good question, and I guess I never talked about it. So in terms of engineering, I sometimes watch George Hotz's videos, okay? So he basically hacked PlayStation when he was a kid because he wanted to play games for free. And then he hacked iPhones in US, in United States, because the iPhones were only able to be used with AT&T. AT&T is a cell service provider. He hacked it so we can use iPhones with other SIM cards. And he does live streams of live codings, let's say 8 hours straight, And I think that's very enjoyable. You know, you sit on the computer and code for 8 hours straight, and something comes out. I like that hacker mindset a lot. Doing things, finding ways of doing things so we can make possible uh, great outcomes to be true. I like that kind of mindset. That's why I can say, I guess, George Hotz. So George Hotz also works on autonomous driving, like Elon Musk. Uh, he tries to develop a piece of hardware so you can attach it on your car, and your car actually does not need to include an automated test pilot. Uh, you just, it is okay for you to attach it and then it works. I think it is very good because Tesla cars, let's say, are being built by Tesla with the intention of being autopiloted. But this little hardware works in every digital car, let's say, basically. Of course, I'm simplifying a lot here. It doesn't work in every case, in most cases, let's say. But it is a good aim. Yes, I guess. Uh, I like that hacker mindset, making things possible, finding ways. Finding ways to do things. If there are no other questions, let's say we wait until 15 and then we close. And also, if you have feedback, you can give it. Like, uh, what was the bad parts of the presentation and what was the good parts? I can get feedback to, you know, make presentations better in the future. It is getting close to 15, and I guess thank you for watching, and it has been an entertaining, let's say, enjoyable stream for me, and I hope it is the same for you. And let's say see you next time, and take care.